wasn't really sure how to prepare this talk. It sounded like it's supposed to be pretty open-ended. Hi, are you ready?
Yeah.
Hi, nice to meet you. Yeah, I'll be around all afternoon if you want to talk at some point.
What's up?
316. In one of these buildings.
Thank you.
Hey, you're welcome.
Generous means general or generic?
It means generic in a technical sense and also friendly.
Ah. So it's a technical name.
It's a technical name, but it's meant to convey something.
Yes. And we are over QL before, not over CL.
Yes, yes, everything is QL rational.
And can you say the content is a little bit more about the content of 7? So do you describe the structure of the packet?
So conjecturally, but classical local Langlands is this meta conjecture, right? That there should be this finite to one map with some properties. I'll describe. There's a precise conjectural way to invert the map if you're given an L parameter and a representation of the centralizer.
Just one for GL2, the traditional Langlands conjecture in the case of GL2 has been known.
Indeed.
And known in very explicit terms. You just have
that's right.
In concrete correspondence, and it's a little bit crazy if the residual characteristic is 2.
That's right.
But otherwise, but even in this case, it's very explicit.
That's right.
But here we want, the problem is that we have a category with a semi-orthogonal composition.
That's right.
Graded, whose graded, say, is associated graded. Is rather simple and known. But somehow they will have this gradient.
That's correct.
And now, and so what is the?
I would suggest maybe we start by looking a little bit at some examples for GL2.
Yes, and maybe you can review the sequence. So my understanding is that you proved the conjecture for GL2.
That's correct.
The question is whether it's the proof is as there are is the so we have two mutually inverse functors, and are they as how to say what is so now the question is how explicit is all this. For instance, it's not clear what explicit means. So the definition of the geometric side involves some black magic, but
that's right.
Something which is black magic. However, the pieces are the graded pieces are explicit, and one can try to describe this huge category by data.
That's right. That's right.
Between very concrete pieces.
That's right.
So one can ask, for instance, how is there an explicit description of this building data?
So my feeling is still that the answer is no, but I only came to this by looking at examples. And so for GL2, there's a precise sense in which there's only non-trivial gluing around a very, very small locus in this space of L parameters. Sort of at most L parameters, there's no gluing. Sort of all the strata don't talk to each other. That's actually what's captured by this term, generous, somewhere on this menu.
Yes.
So maybe we should look.
Okay.
Why don't we start with some examples for GL2 and then.
Okay. So maybe yes. So it's already. So my I think we should follow the chef's language.
Okay. Sounds good.
Recording in progress.
Great. Okay, so some examples. Yeah, let me try to be really concrete and stick with GL2. I mean, some of this would work for GLN also, but let's just consider absolute simplicity. And by examples, like, what do I mean by examples? I mean, we have these two sheaf categories on two different sides, and you can imagine on either side, you may write down some explicit sheaf by hand, right? And then you could ask, can I, comprehend the thing that it is supposed to match on the other side? Okay, so let's start with the simplest case. So let's start on the L parameter side. So I'll let phi in the vector of QP and so GL2 QL bar be supercuspidal. So irreducible. L parameter. So we know that GL2 QP and its inner form, so D cross, where D is the usual quaternion division algebra, right? These both admit a unique, irreducible, smooth representation whose L parameter, which is even supercuspidal. I'll write that in a second. Which is moreover supercuspidal. Maybe here I call it pi. Maybe here I call it rho. And these in turn correspond to each other under the Langlands correspondence.
Maybe could you remind us, so how explicit is this correspondence, and if you have the phi, how explicit is it?
Yeah, great question. So for GL2, it's 100% explicit. There's this amazing book by Bushnell and Henniart. It's called the Local Langlands Correspondence for GL2, and they spell it out in 100% detail there, including the case where phi is 2, where there's sort of some unusual phenomenon on both sides. It's also the case that it's known that this correspondence sort of occurs in nature in the cohomology of this Lubin-Tate tower, right? But for GL2, you can make it 100% sort of a by-hand construction. Given phi, you can write down pi by some recipe. Yeah.
And just to clarify,
Yeah.
It's also true that phi is, so phi is somehow, it's a finite amount of data.
Yeah, phi is a finite amount of data. A typical way you would get such a phi is that you would take a quadratic extension of QP and some sort of nice character of its Lie group, and then just form its induction to a two-dimensional representation of the Lie group of QP.
Yeah, actually, here the story is as follows. So since here it's convenient to replace QL bar by C,
Sure.
by the complex numbers, or even by the unitary group you can do the following. You can consider the image of phi, and you can consider the corresponding map to P showed. Then, as far as I remember, reducibility implies that the image is finite. Yes?
Yes.
I think so.
Yes, I think so.
Then the question is what are the finite subgroups of the group PGL2 over a field over an algebraically closed field of characteristic zero. Then you can think that the algebraically closed field of characteristic zero is the field of complex numbers. Then you can replace PGL2C by its maximal compact subgroup, and this is SO3. And then the answer is, well, no, we have a classification of all finite subgroups of SO3, which basically goes back to ancient Greek. The most complicated group is the one which corresponds to the icosahedral. The icosahedral group is the most complicated, but it cannot occur because the Galois group of QP is solvable.
Right, but A4 can occur.
Yes, but the other subgroups can occur. However, they can occur only if the residual characteristic is 2.
Correct.
And so we have a complete, in some sense, complete classification of such representation. You have to fix an extension, a finite. First, we have to fix a finite extension whose Galois group in the most complicated is 4, and then you have to fix a one-dimensional character of this extension of QP, and maybe a little bit more data because so it's in this sense you can understand how to classify such representations, and then Bushnell and Kutzko basically explain how to construct. Yes, on the other hand, you can classify independently of this. You can classify the cuspidals of cuspidal representations of GL2QP, or you can classify all representations of the Clauterian algebra. Classify in the following sense that they're all induced from one-dimensional representations of certain very special subgroups. Then you have to guess the actual. So you have two explicit sets of data, and then you have to establish the bijection between them. And if the residual characteristic is not 2, then it is easy to guess the answer. There's another question whether the guess is quite correct or almost correct, but this I don't remember. But if the residual characteristic equals 2, then it is hard even to guess the correspondence because on the Galois side you have the group. You should obtain somehow. The important ingredient on the Galois side in the case of residual characteristic 2 is the group A4, for instance. And A4 has order 12, so 12 is divisible by 3. There is no, so that it should involve some cubic extension. And there is nothing manifestly cubic on the other side of the Langlands correspondence. You don't see any cubic extension. So, but at some point, Kutzko did it honestly. After all, Hecke and Langlands formulated property which describes the characterizes the Langlands correspondence uniquely if it is certain epsilon factors should match. So he just computed these epsilon factors and then established everything by hands. I don't remember what was Bushnell's contribution, but anyway, the book. So there were first papers by maybe by Bushnell, but eventually became a book. The book is by about GLA.
It's about GL2. It's kind of for graduate students, but like
For GLA.
at a pretty high level.
Okay.
Yeah.
Okay. Anyway, it's a funny story. And mysterious in the case of residual.
But I'm somehow taking that whole story for granted in this, because the question is like, how does it occur in this funny geometry? Okay, so let's take this as our sort of starting data. So this phi will give me a point. So let me just say stack L bar to be precise. Give me some point in the stack of L parameters. But this point won't be a closed point, of course, because this phi will have some stabilizer group, right? And because phi is irreducible, the stabilizer group in this case turns out to just be GM. So this point sort of factors over the inclusion of a copy of point mod GM into the stack. And you should think of this more general, like helpful psychological notation. You should think this GM is really S phi. It's the centralizer group of phi inside of G hat. Okay? And so then you get this nice closed immersion, essentially called I phi, and this point modulo centralizer into the stack. Okay. And so now there's a very obvious kind of collection of sheaves you can write down here, because this is a BGM, and so you have these weight n line bundles for every n, and then you can push them forward and they'll give you some kind of nice skyscraper sheaves. And so you get a collection. So I phi lower star low n of sheets. X by n and z. And you can ask, what do they match on the other side? So just to be clear, these are coherent sheaves on this stack of parameters for GL2. Okay. So let's answer this. So you get a match on the other side. So let me remind you a little bit about this picture from last time. So pi 0 of this stack is always the character group of the center of the Langlands dual. In this case, the center of the Langlands dual is just GM, so pi 0 of this is canonically Z. Okay. This Z is the same Z that's occurring here, in some sense. And for each n, we have an open point. Unique. Open point in that component. So I drew this sort of elaborate picture in the first lecture of sort of what different pieces of GL2 look like. And so you get this as an open point in the degree 0 component. And then you get point mod T cross as an open point in the degree 1 component. And then the picture is 2 periodic. I'll write one more. Okay, it just continues on like that in both directions. Maybe let me write, I. It's not my usual notation. Let me write I0, sort of I1, I2, just sort of this obvious labeling. Okay. So for each n, I have a point in here. And so here's the proposition. So under conjecture, well, let's say really under the equivalence. This skyscraper, this weight n skyscraper, this maps to something extremely simple. So it maps to in, excuse me, lower shriek, high phi, and it's even. And it maps to in, lower shriek, rho phi, and it's odd. Okay. So the sheaf you get on bungee corresponding to this really just lives at this one point, and it's just this one irreducible representation.
If I take the star push forward instead of the sheaf push forward, will something change?
That's a great question. In this case, it will not change. This is a general phenomenon around irreducible L parameters on the parameter side. They'll give you sheaves on bungee that are sort of cleanly extended from this collection of open points. Their shriek and their star push forwards, which the whole thing will always be the same. So for each point in this the Z index collection of open points, we have this sort of sheaf sitting there. Here's something you can do. You can take their direct sum. Where of course I write pi phi or rho phi according to the parity of n. And so what will this match? So this matches with the direct sum over all n and z. Of these skyscrapers pushed forward from these weight n line bundles. But the direct sum of all these O of n's is just the structure sheaf of GM regarded as a GM representation. And another way to say that is that it's the push forward along this map of sort of this trivial skyscraper here. Right? So if I call this I phi tilde, this big direct sum is just on the nose, I phi tilde. Or let's say real R. Obvious skyscraper. Okay. And now I want to point something out, which is kind of clear on the spectral side and has a nice interpretation on the other side. So Hecke operators act on sheaves on bungee. They correspond to tensoring by these tautological bundles on this parameter side. If I take something that's pushed forward along a map like this, and I tensor it with a tautological bundle by some projection formula, that's the same as pulling the tautological bundle back to here, and then just pushing it forward again, right? But if I pull back to here, I'm just going to get some vector space of some dimension with no further data, except with a Weber action, right? And so when you unwind what all of this means, you realize that the fact that these two things match means that the structures which this is equipped with imply that F phi is a Hecke eigensheaf. With eigenvalue phi. Any questions about what this this set of words means. I can make this even more concrete. So for example, this eigensheaf, I mean, this sheaf is just a sum of these skyscrapers, and these Hecke operators move you from one component to another in a very predictable way. So let me just tell you what this means in an extremely simple case. If I take the Hecke operator of the standard representation, so just the usual two-dimensional representation of GL2, this will move me one to the right. It will move me from here to here, from here to here, from here to here, pushes the degree of the bundle up by 1. And if I apply this, well, this is a two-dimensional thing. So if this is a Hecke eigensheaf, when I apply this Hecke operator, I'm supposed to sort of get 2 copies of this sheaf, right? And when you unwind what that means, say on these individual pieces, it amounts to the statement, for instance, that if I do this I0 lower sheaf to phi5, I get exactly I1 lower sheaf of rho phi. But it's two-dimensional, and its two-dimensionality actually gets upgraded to the structure of an exterior product with a two-dimensional Lie group representation, and that Lie group representation is just phi.
But we don't yet know what the Hecke operator. I'm not sure that I know the definition of Hecke operator on the geometric side. Probably we will learn it from not from your lecture. Did you define this?
No, I alluded
We're
to
not
them.
supposed to.
Yeah.
This is good. We will hopefully learn from the future lectures by Ninja. But so for now, the only way to understand this works out to look at the spectral sum.
That's right. But let me give you a little heuristic though for what Hecke operators mean here. So in usual geometric Langlands, Hecke operator will take you from a sheaf on bungee to a sheaf on bungee, but then you take a product with the curve, right? Because you allow sort of the point where it's being modified to move around, right? Here, Hecke operator will take you from a sheaf on bungee to a sheaf on a funny thing. It's almost bungee times the curve, but the Fargues-Scholze curve is not well defined. But there's this funny aspect of the story that the space of degree 1 divisors on the Fargues-Scholze curve is well defined. People sometimes call this the mirror curve. And in Fargues-Scholze, you'll encounter this again later, they denote this div 1, sort of the space of degree 1 divisors. And then it's a theorem that this product can actually be removed and reincarnated in a different way. Sort of can delete it at the expense of equipping your sheaf with a WQP equivariance structure. And the idea here is that topologically this is actually a point, and its fundamental group is the Lie group of QP. And so to have a sheaf on this times, point modulo of a group, somehow you can forget the quotient here and pull it out into an equivariance. So this is a theorem in Fargues-Scholze. And so the Hecke operators are really viewed as going from here to here. They take a sheaf and they give you a sheaf with a Lie group action. And that's what I'm using when I write this this formula here. I have a sheaf, now I have a sheaf with a Lie group action. Of course, this is not a detailed explanation, but this is how you should imagine that they're behaving.
Is it just well, if you imagine D1 as a projective line, it would be, well, maybe modulo the action of something like a Galois, but there is some higher cohomological thing, or it's just plain point modulo the Weil group.
Yeah, good question. So it's topologically a point, but it's something a little bit, how do I say this? So let me write 2 formulas, and then I'll wave my hands around. So there is kind of a canonical way to present it, which is that you take the diamond attached to the maximal unramified, completed maximal unramified extension of QP, and then every diamond has a canonical Frobenius on it, basically because it's a functor on a category of perfect rings, and you can you have Frobenius on your test category, so you get a Frobenius on any sheaf on that category, and you form the formal quotient by Frobenius. And you can also present it as a quotient of the diamond of CP by the Lie group. But you have to remember that it's a topological group. And so morally what's happening here, it sounds, again, like I'm having some hallucination, but this is really how you should think about it, is that this is behaving like power series over fp in the variable p, and then this is acting in some contracting, dilating way. So this is like a punctured disk over fp, and then this kind of moves you in or out towards the boundary of the disk, and when you take the quotient, you get something compact. So this thing has a structure map towards sort of the final object in our topos, just like fp bar. And in some precise sense, this map is smooth and proper of relative dimension 1. But its underlying topological space is a single point. But if I base change from this to some other algebraically closed field, then I'll really get something sort of one-dimensional topologically. Maybe that's already too much to say, but yeah. The fact that this is not the Fargues-Scholze curve, but is some other thing, is somehow a key sort of strange aspect of the story. Okay. Questions about this example in other
So you're
directions?
saying that the one is called the mirror curve.
Div 1 is called the mirror curve. Yeah, the Fargues-Scholze curve is not well defined, right? You always have to pick a perfectoid to construct the Fargues-Scholze curve, but the mirror curve is well defined. Maybe we can look at another example for GL2, unless there are more questions about this scenario.
Yeah, can I ask something?
Yeah, of course.
So very naive. It seems like this local Langlands correspondence is kind of encoded and Jack Langlands as part of it.
Yeah, that's correct.
And so is this kind of phenomenon also extend to more general group G?
Yeah, it doesn't. Actually, that's the main point of this paper that I wrote with Tasha Kaleta and Jared Weinstein, is to sort of see inside this Fargues-Scholze machinery how things like character relations for L packets on different groups are sort of occurring. So yeah, you can actually push that to quite a far generalization. Yeah.
Sorry, there's also a question from Zoom.
Yeah.
I know you said you want to talk about GL2, but can we hear what happens with GL3 and SL2?
For which kind of parameters? I mean, supercuspidal parameters, I can say something really general, and it's really clean. It's as clean as this example. When you go to more general L parameters, things start getting really weird really quickly. And I want to talk about this sort of what happens around the Steinberg L parameter for GL2. That's somehow the most interesting one there. But let me say something about the general case of supercuspidal parameters, because it's basically as nice. So for general G, but phi from the J group, G hat dual bar. It's supercuspidal parameter. So you're semi-simple with totally G-reducible, semi-simple with open kernel, sort of the strongest set of conditions you could put, and then irreducible in addition. And so then the center of G hat will have finite index. In this group, if you denote S5, so this is the centralizer. Inside G hat with the image of phi. And you should think that this group is the, well, symbolically, I wrote it this way here for a reason. If you think of this L parameter as giving you a point in this parameter space, that point will come with some stabilizer, and it will be exactly this. Okay? So you get the same picture. You have some immersion classifying stack. This S5 into this parameter stack for G. And if I have any irreducible algebraic representation of this S phi, I can regard it as a vector bundle on here and then just push it forward.
And also just to clarify, it's a closed point.
It's a closed point, and it's even a regular immersion, and the component that it lives in is smooth. So everything is as clean as possible. If the group were semi-simple, this would be its own connected component of this parameter stack. This D S phi would literally just be its own component. Okay, so on the other side, the story is similar. So let me recall that this BG basic, by a theorem of Kottwitz, this is a canonical bijection of characters of the center of G hat. Okay. So in particular, given any row, well, if it's an irreducible representation of this S phi, when I restrict it to the center of G hat, it will have to be isotypic for a single character, right? I denote this like B maps to IB. So if I write here S phi IB for the row such that row on the center of this whole group is IB isotypic. Okay, so then classically we expect that the L packets attached to this parameter for the inner forms of G given by these basic elements are exactly enumerated by this set. Okay? So then classically we expect a bijection. You write it like this. So this is the L packet over phi attached to this group GB. And this should be a bijection here. It's phi. So this is explained very nicely in this paper of Tasha Paleta. It's called the local Langlands conjectures for non-quasi-split groups. He explains different forms of the conjecture in that paper. One of them is an elaboration of this idea of Kottwitz, this BG basic parameterization. And in this particular case, everything is very clean, and you expect a bijection like this. And this should depend, again, it's part of the classical story.
Sorry.
Yeah.
I think I missed something. What's the left-hand side?
Oh, this is the L packet for let's say for the group GB QP of this parameter phi. Sorry, this phi was the wrong font. What's that?
Oh.
My apologies. Yeah, my phi is going to be inconsistent. Yeah. So right, classical local Langlands is this meta conjecture, right? There should be a finite to one map with these properties, but you can make more precise versions of it. And one more precise version is that for supercuspidal parameters, if you only look at the inner forms that arise by taking a basic thing in here and looking at its stabilizer, then the packets should be parameterized by these things, and it should depend on only a choice of Whittaker datum. So maybe this, this phi rho goes to like pi rho. Okay. So now I can tell you exactly how this should be realized in the Fargues-Scholze story. Oops, sorry, let me not erase this.
Oh, so you can use a big eraser.
Oh yeah, I forgot about that. Thanks. Alright, I guess I have to erase some of the menu. Okay, so conjecture. So in general, if we apply this spectral action on the Whittaker sheaf functor to the skyscraper on the parameter side attached to our favorite row, it should be exactly the Schriek extension in this point B of this element phi row. Where B is such that row is phi B. Okay. So this is a very clean conjecture. Of course, as a conjecture, this is still kind of a meta conjecture, right? Because this local Langlands is its own thing, right? But this is given to you by nature, right? And so now you can already make classical local Langlands for these things into a more precise conjecture. You should be saying that this will be a skyscraper at one point. That's an unconditional conjecture. If you look at the collection of those skyscrapers, that should have all the properties that an L packet should have. So this should hand you the L packets that you've been searching for in this case. Okay. And I want to emphasize something funny about this. If I take phi to be the trivial representation, then I will get that B is 1, and I'll get the unique psi generic element of the packet. Okay? And so this Whittaker thing is supposed to normalize the correspondence by sending the trivial S phi rep to a unique psi generic thing. There's a funny aspect of this story, which is that we're getting all of them out of this, not just the unique psi generic one. And so somehow the point is that when you are applying this functor, you're taking the Whittaker sheaf and sort of translating it by Hecke operators in a confusing way, and you can have non-generic stuff occurring as subquotients when you do that. So that's why this is sort of possible, even though these can be non-generic. So this is a natural generalization of the true fact that I wrote down in the case of GL2, which is also a known fact for GLN, but in general this is conjectural. And these again are clean extensions. Other questions about this example? Now maybe we go back to GL2 and do something where there's a new strange phenomenon. GL2 Steinberg. I shall also say these calculations are not due to me. These calculations were explained to me by Alexander Bergman and Mali, and also after Supercuspidal. So I'm just telling you some calculations that some other people did and explained to me, but this story is really nice. So, and for simplicity, let me even take PGL2 just to make my centralizers a little smaller. Okay. So then my dual group is SL2. So let me look at this space of semi-simple L parameters. There's a certain funny point in here I want to take and call it X, ST. So this is the point corresponding to this semi-simple. Excuse me, the semi-simple parameter factors over the quotient of the A group by inertia. This is just C. And because our dual group is SL2, now to do something here, I just have to tell you where this goes as a matrix. So that's also my Frobenius to diagonal matrix P minus a half, P and a half. So this is the semi-simplified L parameter of the Steinberg representation, if you like. It's also the true L parameter of the trivial representation. And this is the only point in the course moduli in the image of the singular locus of the fine moduli. So the singularities of the fine moduli stack are all concentrated above this point. Okay. So in fact, let me draw a picture. inside here I have this point. And so what is the preimage of this point? The preimage of this point is going to be L parameters into here, which are not necessarily semi-simple, but which semi-simplify to this, right? And because I'm in a situation exactly where the ratio of these two numbers is p, there can be non-trivial semi-simplifications where the Wegelin operator is non-zero, right? This monodromy operator can really be non-zero in this fiber. And so in fact, this fiber, something extremely concrete, it's just an A1 mod GM. But you have to be a little careful about the weights. So T and GM acts on, say, the variable here. Or say y. Acts through multiplication by t squared. And so what's happening is that this stack of parameters near this point, sort of x st, or the obvious lift of it, it actually has two components. And one of them looks like this A1 mod GM. Do I have colored chalk? Yes. So this is this A1 mod GM, right? And then this other component is somehow less interesting. This is the component where sort of generically, you have a character and its inverse, and there's no monodromy. So if you take the coarse moduli, you just crush this one fiber down.
Sorry,
Yeah.
Who has two components?
Let's say in a neighborhood of this point.
I'm a little bit confused. So which point? So we have on the upper blackboard you have RG which maps.
Here, let me write something more precise. This fiber is actually an irreducible component of this whole stack.
You could just draw the stack.
This was my cartoon drawing of the stack. So this is this fiber. It is its own component. And it meets another component, which is the sort of generic unramified component. And it meets...
Just so
Yeah.
X is X is T XT is a closed point. XG spec is just a scheme.
Yeah, that's right. This is just a QL bar point. This is just a closed point.
Usual point.
Usual point.
And ParG is stacky.
ParG is very stacky. That's right.
Now you take this pre-image
Uh-huh.
and then you claim that's one mod GR. But then you said you are talking about another component of what?
So this pre-image is an A1 mod GM, right? This is just a fiber of this map cube.
Yes.
This fiber sits inside this parameter stack as an irreducible component, and it meets another component.
And what is the image of the other component under the map cube?
The image of the other component under the map cube is that entire connected component of this parameter stack. So let me draw a better picture.
Volodya,
Yeah.
maybe I can
Yes,
explain.
please.
Yeah, you're welcome to.
So we're looking at two-dimensional gamma representations like in the SL2. Yeah.
Yes.
And so you have the unramified representations.
No, this I understand more or less that we have unramified and you have unipotent.
Yeah.
But suppose I don't know what a Galois group is, then
But I'm in trouble.
no, I don't. But you're defining. I just don't understand the formal statement. So we are studying the pre-image of xt. You have this x. Is there
Let me write a better cartoon.
understand.
So in this case, there's sort of an unramified component that looks like the stack quotient of g hat by its adjoint action. Right, because to specify an unramified parameter, I can send Frobenius to anything in this, and then I have to remember its stackiness.
Okay, so what is the, we are studying a particular SG spec is key, yes, or
Yeah, XG spec is a scheme.
and is X, and then it has a point X Steinberg.
Yeah, that's right.
Is it an isolated point?
No, so XG spec, so there's a component that just looks like the Chevrolet quotient of G hat. It sits inside there. Its preimage in this case, the preimage of that component has two irreducible components. One of them looks like the fine quotient of G hat by its adjoint action, the sort of true adjoint stack.
Okay.
And that meets another component, and that component is the fiber.
Okay, so I just I want to understand. So Matt explained the origin of the story, but I want to formally understand the answer. So, we are looking at a particular component of XG spec.
Yeah.
X Steinberg is a point on this component.
That's right.
But what is the whole component containing X?
It's the adjoint, the GIT adjoint
It's
quotient.
just SL2 course,
Yes.
SL2 modulo conjugation in the sense of geometric invariant theory.
Exactly.
Is it their final? So we are looking at traces of matrices.
That's exactly right. So it's an affine line, basically.
It's an
That's right.
affine line.
That's exactly right. But
and okay.
and then here I drew its preimage, which is a little more complicated, right? Its preimage has an obvious component, which I think Matt was alluding
It
to.
has three components.
What?
What is that unramified twist of Steinberg?
Oh, please let me ignore that. Yeah. There's another fiber. There's another point like this where there's a similar fiber, but let me ignore this for now. I drew some Zariski neighborhood of the part I'm interested in. Okay.
Sorry, can you also so part G or this part of part G is parameterizing Galois representations into SL2. Is that right?
I mean, the whole thing is parameterizing representations into SL2. I mean, here's another thing I can write that might help some people. The stack always has a union of components that deserve to be called the tame components, and this you can present in some extremely concrete way. So this is pairs like G and U in G hat squared, such that G inverse is U raised to the power of P, and then quotient by simultaneous conjugation. Okay. So what I drew is a further connected component of this. Okay. And so you should think this is like Frobenius, and this is like where the sort of topological generator of tame inertia goes. Okay.
And sorry, that's a closed substack.
It's an open and closed substack.
Open and
It's a union of connected components.
And those are the ones that the representation of the factor through the.
Exactly, the ones where it factors through the tame quotient of inertia. Yeah. Okay. But let me just summarize in words what you should take away, because I want to write down some sheaves now, right? That there's this interesting component, which I think of as somehow vertical, whose image in the course moduli is a single point. And this vertical component parameterizes Wegelin representations where the phi part just looks like this sort of Steinberg thing I wrote down there. But then n could be either 0 or not 0, right? And somehow this part, this sort of part here, this is like the locus where n is not 0. And then it degenerates down to where n is 0. And where n is 0, it makes the other component. Okay?
And sorry, I mean, should think of this as like you have a reducible representation, and it's like you have a family of reducible extensions that specialize to
Something
You're
like this.
looking at something where along the horizontal line, U always has trivial image SL2.
Exactly.
But along that vertical line, G has eigenvalues whose ratio is P.
Yeah.
And so U can be trivial still, or it could be like a Jordan block. And so that vertical line is just at kind of 1 star 0, 1.
Right.
And the coordinate of the vertical line is star.
Yeah, that's exactly right. Okay, so maybe let me go here.
Yeah, I mean inside the par tame, there's a connecting component which is a par unipotent, where U is actually got unipotent image, and that's what that two lines crossing is a cartoon.
So let me write H for this immersion of this sort of vertical fiber into this stack. Okay. So this has some obvious weight and line bundles, right? Let me write Ln for H lower star with the usual sort of weight n line bundle on this A1 mod GM. But let me remind you that the weight of the action is a little bit funny, right? The T in GM acts through weight 2. Okay. So this is for all Z. And so we have some canonical exact sequences. So first of all, if you think about the case, say, where n is 0, you just get the structure sheaf. And when n is 2, you get the ideal sheaf of the origin inside here. And the quotient will be some kind of skyscraper at the closed point in there. So in general, this translates into the fact that you have short exact sequences L n plus 2 injects into L n injects into, let me call this delta n. So this is H lower star of the obvious weight and skyscraper. At the closed point in this stack. And there's another thing which is maybe a little harder to explain in a talk, which is that there's more maps between these than there are between these, exactly because this will meet this guy at a point where this thing is actually singular. And so this other component will give you more maps in the derived category of sheaves on here. So there's also canonical maps. Ln plus 2 shifted by 2 in the derived category. So no one's right. Okay, now I can finally tell you some matching sheaves.
By the way,
Yeah.
Is all this written somewhere?
Yeah, so this guy Alexander Bartolome is on the faculty at BU. So if you go to his website,
And Bertolini Meli is one person? Or
it's one person, yeah, with a unhyphenated 2-word last name. Yeah, if you go to his website, he has some 10 pages of notes on.
Is this not also
Sure.
explained in our AGS notes?
Is it? I don't know. In this level of detail? I mean, he writes down every automorphic sheaf that should sort of match every sheaf you should guess on the spectral side here. So, yeah. It's certainly related to some calculations that you've thought about. Yeah. Okay, but let me tell you some matchings. Also, some parts of it are in this paper of Wiggins on the derived category of Hecke algebra.
Yeah, but that paper is kind of mysteriously complicated to sort of fairly easy fact.
Okay, no comment. Okay. Right, so now on the other side, remember I'm doing PGL2. So I have 2 open points now. I don't have a z's worth because when I go from GL2 to PGL2, I somehow kill the translation by 2 structure that we were having. So I have one open point that looks like point mod PGL2. I have another open point that looks like point mod the projectivization of the units in the division algebra. Okay. Right, so this. Let me now switch back to my usual notation. So I write I1 for this point, the immersion of this point, and I will write I1/2 for the immersion of this point. The 1/2 is, yeah. a mental stand-in for the slope of the isocrystal that gives you this particular interval. Okay, so proposition. So under the categorical equivalence, the following sheaves match. So, at this open point, I have the Steinberg representation of PGL2. I can Schrieg extend it to all of 1 PGL2. That will match exactly with what I was calling L0. And this L0 is just the structure sheaf of this fiber, of this cube inverse X, ST. Okay, so the structure sheaf of this preimage of this one point downstairs actually matches with the Schrieg extension of this Steinberg thing. The trivial representation at the other open point, right, which is sort of the Jacques-Langlands correspondent of Steinberg, if you like, this matches with L1 on the nose. Okay, there's a third one I haven't mentioned yet, just the trivial representation of the split form of PGL2QP. This manifests the fact that the categorical equivalence is typically not T-exact in any naive way. And so this will map to L2, but shifted so it's in homological degree -1. Let me write one more, which is that I could do the induction from the Borel up to PGL2 of the modulus character to power 1/2. So this will have Steinberg as a sub and trivial as a quotient, if I did the exponent correctly. And this will match with delta 0, this skyscraper. And let me just dwell on this a little bit more. So I told you this has Steinberg as a sub and a trivial representation as a quotient, so you get a sort of short exact sequence. Steinberg. Reduction from Borel to G, delta 1/2. Trivial. This maps to a triangle. L0 goes to delta 0, goes to L2, 1. And this is actually just the rotation of an instance of the first short exact sequence that I wrote there, which is just it's a rotation of the short exact sequence that I already wrote. 0 goes to L2, goes to L0, goes to delta 0. Okay, so you can already kind of see that things are not going to be T-exact in any sort of naive way. I feel like this Schrieg from 1 is sort of embedding the abelian category of smooth PGL2 reps fully faithfully in sheaves on Bungie. This already shows you that, when you compose that with going to the other side, you're not going to get something that's T-exact in a naive way. Questions about what I've written so far? I want to dwell on this a tiny bit more because there's something much funnier you can do with this example. So I can set f plus to be the colimit. I didn't tell you where these maps come from, but there are canonical maps from Ln to the 2 shift of Ln plus 2. So you can take the colimit, but in quotes, of L0 goes to L2. This is in quotes for a reason, right? Because objects of int co, right, are not true colimits, right? They're sort of formal inductive systems of coherent sheaves. So this makes perfectly good sense as an element of int co. And it's genuinely incoherent. If you project from int co back to q co, well, each of this stuff is drifting further and further to the left, right? And so when you project, you'll have 0 cohomology in every degree. So this is actually 0. Okay, so this f plus is actually non-trivial. You can check, for instance, that its endomorphism ring is just QL bar. This f plus matches the constant sheaf. On the degree 0 component. There's also a version of odd parity where I can start with f with L1 and then L3 to L5, 3, blah, 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 up to a shift that would give me the constant sheaf on the other component.
Sorry, I forgot. What is C?
C is this general projection you always have that sort of takes an incoherent system and formally takes its colimit, so it maps you back to Hugo.
So it's capital C.
Capital C, yeah. That's right. So this is really sort of, it's genuine in some sense, right? It lives at minus infinity in this non-left complete T structure of int co. Yeah, I'm certainly not going to try to prove any of this. This is just meant to be sort of a gallery of strange beasts.
No, is it written in this?
Yes, it's written in his notes in these.
In the notes of email.
Yeah, I can send it to you after the lecture today if you're curious.
But they are available on his.
They're available on his website. It says something like some calculations around the Steinberg parameter for GL2 or something. It will be very clear which document. Right, and actually he did all these calculations before we really began this project trying to prove anything. And these calculations were somehow conjectures last summer, and they were sort of a key source of motivation for us to actually think about trying to prove this stuff. What's up, Matt?
I don't know, there's these calculations, they're kind of, I think, I call them well known. I mean, you can kind of see them from Taylor-Wiles' patching.
Okay.
So, not the F plus one. But I think the other calculations are kind of...
Yeah, I think these were also known in some sense to people like you and Xinwen.
And Logan, I'm sure.
Right. So I think part of the novelty here is that he sort of went into genuinely incoherent territory with things like this F plus and other.
Yeah, the F plus is...
Right. I mean, you can also ask sort of other things, like you can ask, what do I get if I take the star extension of Steinberg? Turns out this is not a clean extension anymore. And this, it turns out to have non-zero sort of stalks at every point, and it's kind of strange to describe it, but he also writes down the thing that this should match, for example. Yeah.
So it lives on the whole. Does it live on the whole?
Yeah, it lives on every single point that is a specialization of the open point. Yeah.
And it also has a kind of colimit, like it has some kind of description probably.
Yes, there's a whole bestiary of sheaves in these notes, and you have to build certain of them before you can build others, and this one comes rather late in the story. So, yeah, it's only 10 pages though, these notes, so I recommend it. Other questions about this Steinberg thing? I'm tempted to mention one more thing. Maybe I can erase this. So let me just redraw this cartoon. So here's my A1 mod GM. But remember, I had a weight 2 action on this. So the open point is not just trivial point with no stabilizer. The open point is the classifying stack of mu2. Right? And so I get some canonical map point covering mu2. And then this sits as a locally closed immersion inside this parameter stack. Right? It's sort of open in this irreducible component, and then that component is closed in the whole stack. So maybe this is mu2. That's inside the whole thing. And if you take the push forward along this of, let's say, the obvious skyscraper here attached to the trivial representation, or the obvious skyscraper here attached to this sort of sign character of mu2, this sort of tautological character, this will actually just be something very explicit in terms of these L's, right? Ln sits as a sub-line bundle of Ln minus 2, and when you realize that all you're doing here is pushing forward from, A1 modulo the origin into A1, and you work out what's happening with the weights, you realize that this is the colimit of Ln sitting inside L minus 2. Blah. Let's say 0 minus 2 minus 1 blah blah. And then this is the limit. L minus 1 sitting inside L minus 3. 1 minus 1. So these are both quasi-coherent sheaves. Somehow they're at the opposite end of the spectrum of bad behavior from this F+. They're really quasi-coherent sheaves in degree 0 in the standard T structure.
So you are the chef, and
Yes.
we are
Being subject to a menu.
yes, we are subject to something very delicious. But the problem with me is that I'm pretty full in this direction.
Okay, great. That's great.
It's very interesting.
No, that's fine. One can have too much of one dish, for sure.
Yes, but maybe we can come to
A different course.
Consider the dessert.
Sure. I'm happy to do this. Let me mention one final thing about this example, just to tie. Why did I put it
But
on
the
the board?
important thing is
Yeah.
that Dr. Mele wrote this up
Yeah, that's right.
perfectly in his 10-page.
That's right. And it's a very nice collection of
People
examples.
who have reasons to try to understand the technicalities can just read these
Yes.
10 pages.
That's right.
Okay, so what can we? So you discussed the Steinberg parameter, and did you already discuss the trivial parameter?
No, I did not, but it may be too much of a similar dish.
This is a similar dish.
Yes.
In ordinary Langlands life, the trivial representations of Steinberg live together, so to say. So they.
But the trivial L parameter is a different story, right? That corresponds to the...
trivial L parameter is it's not trivial representation.
Right.
And are you saying that it's a little bit special?
It's a little bit funny, yeah. Maybe I can tell you something very short about it. It'll be a
Is there
cleanser.
anything funny about it in the classical? Maybe it's a little bit funny for Essel too. So what's funny about the trivial parameter?
Right. By the way, let me end one more sentence about this. The sum of these two things corresponds to a Hecke eigensheaf, whose eigenvalue is the Steinberg parameter, not the semi-simplified Steinberg parameter. And that eigensheaf turns out to be perverse and extremely nice. And it's in fact a tilting perverse sheaf. It's not made from intermediate extensions. It's not as far from intermediate extensions as possible. But enough of this. You can read all of this elsewhere. So what is special about the trivial L parameter, let's say for GL2 or PGL2? Aside from this Steinberg and its twists, it's the only point where the fiber of this coarse moduli map is interesting. At most points, this coarse moduli map is not really doing much.
Yes, and
But at the trivial parameter, like the issue is that we never enforce Frobenius semi-simplicity in our definition of this parameter stack. And so you can send Frobenius to any unipotent element to get something in the fiber. But then you quotient by G hat. And so the fiber is really the nilpotent cone modulo G hat. Let me write a very abbreviated version, not too much detail. So let me write X triv in this space. So this really means the point corresponding to the absolute trivial L parameter, everything in the Vega group goes to 1. So then the fiber their Q is the nilpotent cone for the dual group modulo G hat. Right? And this nilpotent cone modulo G hat, so this has a rich period of coherent sheaves. Yes, we're cutting it up. I can spell it, Kavanagh and other people. And the very, very, very short version is that some of the sheaves that he wrote down and thought about for certain reasons, they match under the equivalence with very explicit sheaves on the other side. And these sheaves they're not as trivial on this side. They can be concentrated in 2 cohomological degrees, say, for GL2. And this also gets into this question of whether T structures play a role in this whole story. Part of what Bazarkovnikov did was he investigated this perverse coherent T structure on sheaves here. That actually turns out to match some intrinsic T structure on the other side. So that's the very short sort of palette cleanser. Now we can go in whichever direction you wish.
and what is general? Okay, maybe what is a generous parameter?
This has a very simple answer. These are, and I can tell you why they matter. Okay, so for supercuspidal parameters, I was telling you earlier, these things tended to be cleanly extended, right? You can ask in what generality does that phenomenon persist? This class is meant to capture exactly that. But here's the definition. So let's say phi is a point in here. So it's one of these semi-simple L parameters. Okay. Phi is generous. If the fiber over this point, up to some tiny ambiguity, maybe I say the reduced fiber, if it's as small as possible. Because phi itself will always give a point in the fiber, sort of the unique closed point in the fiber. And so you'll always have BS phi sitting as a closed substack of the pre-image of any phi here. And you can ask, is it the case sometimes that there's nothing else in the fiber, right? So this corresponds morally to phis which are semi-simple, and they cannot be unsemi-simplified in any way whatsoever. The fiber over them is just that one phi that you started with. There's no room for something to degenerate to phi.
Yes. So which are generous in the case of Sheaf?
Yeah, great question. So if G is GL2, so then phi is generous if and only if phi is not of the form chi twisted by norm. So this is the Steinberg, this is the sort of twist family of the Steinberg parameter. Let's say and phi is not of the form the same character twice. So twists of trivial and twists of Steinberg are the only non-generous things for GL2.
Okay, so in our situation, 4, so
yeah.
Is everything which is not 2 and 3.
That's exactly right for GL2.
For
They're
GL2.
mutually.
Yes.
enveloping of everything, and they're disjoint. That's right. For other groups, they're intermediate phenomena. But for GL2, you have this nice dichotomy.
Can you classify them for GLN?
Yeah, absolutely. So for GLN, let's say phi generous. If and only if phi is a direct sum, let's say I can express it as a direct sum, phi 1 through phi d, right? With phi I irreducible and pairwise distinct. And phi I is not the one twist of phi j. Okay. So furthermore, this is it looks a lot like this decomposed generic condition in the first Fargues-Scholze paper, if you're familiar with those words. If that doesn't help, then ignore. But it's some very strong generacy condition.
So and then you said that these are that for generous clean.
That's right.
Cleanness statement.
That's right. So so heuristic. This is how you should think about it. So at generous phi sheaves on bungee. Kind of direct sum of the sheaves on bungee. Remember, these were just representations of the stabilizer group. In general, there's complicated gluing happening across these different strata here, but let me put some precise symbols so this isn't nonsense anymore. Last time we talked about these finite sheaves. They're the ones that sort of have finite length in some very strong sense, and this is literally a true conjecture. This is a conjecture. Just or GL and modulo, a bunch of writing.
No.
Yeah, so yeah, all gluing is trivial. Let me just write this slowly.
No, there is something mysterious called number 7 in your menu. Precise classical local language conjecture.
This I already gave you a flavor of in this supercuspidal discussion.
In what sense? So, what does it mean for GL2?
For GL2, it amounts to things I've already said.
But
Yeah.
Classical.
I can say something.
Are you saying that there is something which was unknown, let's say, to Bushnell?
Well, so classically, local Langlands, right? In this formulation I'm using, we have a pair where I have a basic B, and then a pipe, a representation of GB, right? And classically, we expect that there's some finite to one map from pairs like this.
So the question is, for instance, what corresponds to the other strata, which non-basic strata?
That's right. That's right. And so there's a good answer to this. But then you can even conjecture, moreover, that this spectral action, this is now for totally general groups, that at certain parameters, the spectral action tells you how to invert this arrow in an extremely precise way. So this is written, maybe I should have mentioned this. There's some notes on my website where a lot of this is discussed. Beijing notes. So many of these things are discussed in these notes. In particular, this precise classical thing.
Here is something which makes so the geometric side is so to say very rich, but it's also, well, its rigorous definition involves a lot of hard mathematics,
Mhm.
periodic mathematics.
Mhm.
Now, is there a hope to define some kind of? On the other hand, it seems that is there a kind of toy model of the geometric side? For instance, in the most, for instance, you have this Steinberg parameter story,
Mhm.
and here is there a way to? So first of all, the whole theory tells us that on the geometric side you have a splitting into the direct sum of pieces, and most of them have a simple structure because they correspond to generous parameters.
Exactly.
So let's consider the interesting part which corresponds to the style. Is there a way? So it's just direct summand of the categoricality of bunch.
Mhm.
Is there a hope to describe the same direct summand without, in more humane terms, without all this hard periodic stuff?
Some additional kind of equivalence of categories. Maybe there's like a simpler geometric toy model for that category of sheaves, or something like this. That's a really good question. I don't think I have a precise
okay, so
answer to this.
at this moment,
I think the answer.
there is no candidate.
Matt, do you want to say something?
No, I just confused which side is the hard.
And the
Can you describe
geometric,
the hard side?
so the spectral side, at least the definition doesn't. The good thing about the spectral side is that I don't have to read Scholze's Berkeley lectures. I don't have to read from Fargues-Scholze. So this is beautiful and great mathematics, but my life is finite, and unfortunately it's very finite. So, but for the spectral side, I don't need it.
Sure, it's a more
question
classical
is
nature.
Is there, if I'm interested only in the, let's say, in the non-general, for people in the case of GL2, the non-generous part, the non-generous direct summand of this D of G is pretty small.
That's correct.
And is there, and one would like to have a description of this geometric side, of this direct summand of the geometric side, which is doesn't involve, which makes visible all the structures which have in the sophisticated picture, for instance, the strata labeled by P of G and the various functors and so on, but which doesn't use sophisticated periodic mathematics.
Right. I think this is a very interesting question, but I don't have a good answer for you.
So there is no candidate.
There's no candidate for a sort of precise
and maybe
model that's simpler.
People are currently so happy with Fargues-Scholze that they don't even work.
No, it is a good question because, as you say, setting all of this up is extremely technical.
Yes.
And to some degree, you can treat the technicalities as a black box, but like, of course, it's not satisfying to have to do this. So Xinwen-Zhu has another approach where instead of working with bungee, you work with this stack of isocrystals with G structure, which you can carefully make into some kind of FPQC stack on perfect rings as opposed to some perfactoid rings. And that is also going to have some category of sheaves that are glued from the same, exactly the same pieces And even the whole category should be equivalent. So this is ongoing work of Landis and Ian Gleason, like proving that the category of sheaves on this ISOC thing agrees with sheaves on this bun thing. But this ISOC is also a bit frightening when you stare at it. You realize that there's non-trivial relations, like closure relations between strata, but every stratum has dimension 0. At least in bun G, the strata have increasing negative dimensions as you go down, so somehow it feels humanly reasonable that they have closure relations. This other thing is somehow scary in its own ways. So, but its test objects are more familiar, it's just perfect schemes. So maybe this is some partial answer.
And isocrystals really mean F isocrystals over perfect. So
That's right, that's right.
Mhm.
Yeah, I mean, you do something like, you form the adjoint quotient of LG by, like, Frobenius twisted LG, where LG means like the Witt vector loops.
Yes. So the plan for the seminar is that we will have a series of eventually.
Yeah.
Maybe in November we'll have a series of talks by Dennis Deitzko and his collaborators who did probably something like Sheaf and Shoe, but in the case of equal characteristics, and they use, in this case, they can use Stukas to construct the spectral action. So conjecturally, their category is the same as the one of
That's right.
Fargues-Scholze, and
That's right.
conjecturally the spectral action is the same. But technically, however, they can treat only the equal. I vaguely, is it the whole menu, or there was a part of the menu which I think there was something about Shimura.
There was some bits that got erased from the menu. There was
Yes,
3
I
items
think
that
there
got
was
erased.
something about Shimura.
Yeah, there was something about Shimura varieties. That's right.
Yes.
Both local and global.
Yes, and let us stick to the case of GL2.
Okay.
In this case, I hope that Shimura just means global Shimura means moduli for elliptic curves.
Okay. Let me think. Can I say a little about the local story first? It's related to things that I think.
Yeah. So what
will
are
help.
the titles of the menu there?
Oh yeah, the 3 erased titles were the magic wand conjecture, cohomology of local Shimura varieties, and cohomology of global Shimura varieties.
Okay, so and anyway, this is the Shimurian. There are several parts of the menu which are related to Shimura varieties. This or that. And what do you mean by local Shimura variety?
Right, so local Shimura varieties are a generalization of things like Rappaport-Zink spaces, moduli of p-divisible groups with some structures. But it's an abstraction where, just like with Shimura data, right? Shimura examined all these examples by hand and constructed canonical models by hand for many moduli spaces of abelian varieties of structures. And then Deligne abstracted it into this very conceptual group theoretic definition, right? So a similar thing has happened with this Rappaport-Zink story. So now there's this definition of a local Shimura datum. I can tell you what this is. Definition.
Just one general remark.
Of course.
An important fact about Shimura variety is that well, in the Shimura data there is a certain co-weight. The co-weight has to be minuscule, and this is because forced upon us by Griffith's transfer set.
Indeed.
In the so on the other hand, and for instance, in the case of E8, there are no minuscule.
Indeed.
So somehow Fargues-Scholze beautifully overcomes this Griffith's transversality issue. Now, in this, you are going to explain some kind of Shimura data. Is there a minuscule assumption there?
This is a really good question. You can impose it, and then you'll get a restrictive notion,
Yes.
but with the benefit that your objects will be rigid analytic varieties. They will be of a classical nature
Rather than diamonds.
rather than diamonds. That's right. But you can also not impose minuscularity at the expense of working with some diamonds instead. Which
I
are we
see.
vegetarian or are we having the meat course?
Okay. I think both. Just
Okay.
a moment. So you are saying that there is a diamond version,
Yeah.
which, however, is not the same as bungee.
It's tied into this bungee story in a way that I hope I can indicate. Yeah.
Yes. Okay.
So let me make a simple.
So maybe both local Shimurian versions.
And then this more wild diamondy thing. Okay, both versions.
Let's start
Let's
with
see.
the
Okay, so let me present the definition in two parts at once. So let's say a triple. So let me try to present this like okay. Here's how I want to arrange it. So a local Shuka datum. It's a triple. And let me just remind you throughout these lectures, I'm always assuming my group is split, but of course there are more general versions of these definitions which don't impose this restrictive condition. So it's triple G mu P, where G is as usual, so it's some connected reductive. And for simplicity, I'm assuming split, but you don't need to assume this. And mu.
but G is over QP.
Yeah, G over QP. That's right. Mu from GM into G is a conjugacy class of co-characters. And B is an element of this Koppitz set, which is sort of constrained relative to mu in the usual way. It's in this Koppitz set BG mu, right? So its Newton polygon is supposed to lie on or below the Hodge polygon of mu, and they meet at the endpoints. That's the intuitive meaning of this.
Just a moment. So we the triple which is adapted with QP mu GN.
And let me give a second part to this. So if mu is minuscule, give it a different name. In this case, we call it a local Shimura datum.
Again, what is the definition of BG mu?
Yeah, let me remind you in the simplest case where it's interesting.
Is it a subset of BG?
Yes, absolutely a subset of Kowitz's B of G. So let's do GL2.
But what is the definition of BG mu?
So it's the elements B in B of G, such that, so remember an element B had these two invariants associated with it, this Newton
Yes.
map and then this Koppitz map. And the target of the Newton map was co-characters into, well, the way I set it up, it was dominant rational co-characters into the torus. I can always conjugate this to a dominant rational thing.
Yes.
And so then you impose that the Newton point of the
Some kind of inequality. At this moment, the direction of the inequality is not important. So
right, it's that it's some Newton lies below Hodge condition. That's the intuition, right? And also that there's some relation between the Koppitz maps. This mu is a character into G, so it's also a character of the dual group. If you like it, then you can restrict it to the center, and then you have to ask if the Koppitz map be the same. Koppitz might be the same. But there's really just one example you should keep in mind. Like if G is GL2 and mu is the usual sort of simplest non-trivial covariant, so 1, 0, right? Then the only B's in here are the sort of isocrystal given by B is p comma 1. So you have a slope 1 piece and a slope 0 piece, each with dimension 1. And then there's also the isocrystal of slope 1/2. And that's it. So just 2 elements, right? And this, I think Kowitz was interested in this set, right? Because when mu is the Hodge co-character of a global Shimura datum, this is exactly supposed to parameterize the Newton strata in the special fiber of the global Shimura variety. So this was invented for global means, right? You should think in this case, this is like a ordinary and super singular.
So all this is kind of combinatorics,
Yeah.
whose goal is to say something or to understand something about the modular of elliptic curves.
Right.
What we're trying to do with the modular of elliptic curves?
So, sorry, let me come back to that. Sorry.
Can I have two basic questions? So,
Yeah.
Sorry, so in the GLN case, is the second condition just that the endpoints are equal?
Yeah, and in the GLN, and for many groups, this condition implies this condition, but for GLN, yeah, you just need the first condition.
Okay.
Yeah. And did you say you had a second question?
I just feel like the inequality is flipped. I'm not sure.
Well, I think I want this to be. No, I think it's actually okay. I want this to be sort of straighter than this, which means this should be this plus some dominant weights with rational. Yeah. Yeah, I think it's okay. I mean, if you're actually drawing polygons, then different people have different conventions, but I mean, you take dominant representatives, and then it's all okay. Okay, so what does this have to do with geometry of any kind? So given such triple, so Scholze, Weinstein. Fine.
Such triple means local Shimura.
Yes, exactly. A triple like this, G mu V. They defined a tower, and let me just be elusive for a second. Let's say spaces.
And so far there is no minuscule condition.
Yeah, and if mu is minuscule, you give it a different name because you should think of it in a different way.
And what's the name in general?
The name in general is local Stuka datum. And when mu is minuscule, it's local Shimura datum. Right, so you define some tower of spaces indexed by K open subgroups in GFPP. And this is some, I don't know how specific I want to be. Let me say generalizing. Let's say the usual towers coming from RZ spaces. Right, so if you have a Rappaport-Zink space, right, it will be some moduli of p-divisible groups with some structure. But then over its generic fiber, you have the Tate module of the universal p-divisible group, and you can start trivializing the Tate modulo p to the n, or modulo something. And as you go up and up and trivialize more and more, you get some tower of rigid analytic varieties. And this is what people mean when they speak of, the Lubin-Tate tower or the Drinfeld tower or things like this. And this is meant to be some sort of ultimately general version of these towers. And so let me be very concrete now. So if G is GL2, mu is 1, 0, and B is the slope 1/2 isocrystal, right? Then this is exactly the Lubin-Tate. Tower.
And for the other B?
For the other B, it will be some moduli of ordinary p-divisible groups,
Which is
not as interesting.
Not.
It's still there, but it's not as rich somehow. Yeah. And if mu is minuscule, these are rigid analytic varieties. And they're even smooth. Let me say that.
How is the condition that mu is minuscule?
Yeah, that's a
analytic varieties?
That's a great question. So the way that they construct and prove these. So first, let me say that they define them a priori in this larger category of diamonds, right? Diamonds contain rigid spaces, right, in a way that's compatible with the tall maps. And so the proof, the construction of these is as follows. You first construct them as diamonds. Then you show that there's a funny period map out of them, this analog of this Gross-Hopkins or Grothendieck-Messing period map. Some different people call
You're
it.
discussing Scholze-Weinstein.
He was asking how do you prove that? How do you not Rappaport-Zink, but Scholze-Weinstein?
And by the way, what is the approximate? How do I find that paper?
Yeah, this is in the Berkeley notes. They're Berkeley lectures on p-adic geometry. Let me just try to say this concisely. So they prove that there's a generalization of this Grothendieck-Messing or Gross-Hopkins period map, whatever you want to call it, whose target is a Schubert cell in some funny version of an affine Grassmannian, one of these de Rham affine Grassmannians. And this period map is always étale for any mu. And then they prove that for minuscule mu, this Schubert cell is actually a rigid analytic space. And so now you have a diamond which is étale over a rigid analytic space, and this passage from rigid spaces to diamonds is compatible with étale sites. And so that means that it actually has to come from a rigid space. So it's extremely inexplicit.
So the computation happens in this affine Grassmannian.
That's right.
This
That's where the deep part of it is that some Schubert cell is actually like a classical rigid space.
So maybe a related question, or maybe something like this is that, I mean, these objects are defined as diamonds, so
Yeah.
they're defined as moduli. These objects are defined as moduli problems, right?
Yeah.
So they're defined as moduli problems on perfectoid space.
That's right.
But
Well, in the limit they are. For fixed k, it's actually awkward, but yeah. yeah.
Oh, okay. But saying that it comes from a smooth rigid analytic space is also saying that we can like evaluate it on a larger class of objects.
That's right.
In particular, can talk about like a tangent space and so forth.
That's right. That's
And
right.
Is it possible to say what is a functor it represents on more general objects or non-perfectoid objects?
So as they construct it, it has. Let me write something on the board and then come back to this. So as I said, they built some tower. You can check the limit over the whole tower. So this is some object at infinite level, right? And this has a clean moduli interpretation. So this is the functor. So this is the space modifications. Now you start to see why the word Stuka may be appearing somewhere here. It's something about modifications of vector bundles. It's modifications from the trivial bundle to the bundle parameterized by V. Meromorphy, say less than equal to V in the appropriate sense. So it's not at all clear this has anything to do with Rappaport-Zink spaces in any case, right? That's its own set of theorems that if mu is minuscule and the datum is sufficiently nice, this is related to moduli of p-divisible groups. This is also proved in the Berkeley lectures. Right, and in general, this is just some diamond, and I think what Akil was asking is that once you know that these things are rigid spaces, like, can you define them, their functor of points, say on like other rigid spaces? I think this is actually, not a good satisfying answer to this question right now. Because the way they build it is they build this first, they prove it's a diamond, then they formally take the quotient by k to get one of these, and then this has some period map towards the thing you understand, and that thing you understand is a rigid space, so then you get that it's a rigid space, and it's very inexplicit, right? But it's analogous to the fact that like a general Shimura variety is not really a moduli space of anything, right? It's just some canonical descent of a complex algebraic variety to some number field, right, that you do using special points. But you don't really have a moduli interpretation for these E7 Shimura varieties, for instance. I would say this is of a similar flavor right now. And if you want to know about their tangent spaces, like you can actually do that up here, but you should ask Sean how he knows that. He's inventing a theory of tangent spaces for things like this right now.
But, I mean, also, I guess you said it was all over something that was more explicit.
Yeah, so these individual spaces, these admit some tall period map towards a Schubert cell in a B de Rham affine Grassmannian. This is some analog of this Grothendieck-Messing period map, right? And then when mu is minuscule, this is actually a rigid space, and that forces these to be rigid spaces. That's the strategy of that argument. But let me say something about, like, why am I even mentioning these?
Yes, and maybe a related question is what is this? Is there a relation between these Stuka varieties and bunch?
Absolutely, absolutely. Let me erase this. Let me mention also one more thing before I answer that question, which is that on this tower, there's sort of two groups in the picture. There's an action of GB, right, on sort of every level of the tower. Classically, this corresponds to changing the quasi-isogeny, right, to your fixed sort of marking p-divisible group. And then on the whole tower, you also have an action of G of QP, right, but that sort of moves around different layers of the tower by sort of Hecke operators, if you like.
Yeah, for instance, in the most classical example, GP is the quaternions, and
Exactly.
PP this is the example I learned.
That's right. That's right. And that example is still of relevance here. And I can tell you how that example occurs in bungee. So here's the theorem. So this is in Fargues-Scholze. So with care, you can make sense of the cohomology of this tower. Oh, let me actually do a fixed K. Let's not even take the colimit. Let's just focus our attention on one layer in this tower. So this is some maybe smooth, rigid space if mu is minuscule, and so it should have some atomic homology groups. And these should come equipped with some action of this group GB, because that acts on every layer of the tower individually, right? And it was classically very hard for people to prove anything about these groups, right? Any kind of finiteness or boundedness properties or anything like this. Here's a formula. These are the stalks of some Hecke operators applied to some sheaves on bungee. Oh, sorry, and these Hecke operators have a shift and stuff built into their definition, so I should probably put that here. So the dimension of these turns out to be the pairing of two rows of mu. So at this open point in bungee, right, any representation of G of QP gives you a sheaf at that open point. So you can take this sort of compact induction from K of the trivial representation, and then you Schritt extend to all of bungee. And then if you apply the Hecke operator labeled by mu, and take the stalk at this point B, this string of symbols, when you unwind it, it actually gives you the cohomology groups of the layers in this tower. Okay, so it was a conjecture, for instance, that these cohomology groups are finitely generated as representations of GB, which is not obvious because these spaces are wildly non-compact. And this conjecture actually is an immediate consequence of this formula, once you know enough about how compact sheaves on bungee behave.
But also just to reply to this formula, this formula also relates to the formulation that that the space of group is like modifications.
Yeah, that's right. Because when you think about what Hecke operators on bungee are doing, right, it's really just a moduli of pairs. We have a bundle and a modification of the bundle, right? And then somehow these two operations amount to trivializing one of the bundles to be the trivial bundle, and the other one you force it to be the bundle EB. And when you stare at what these symbols are doing, this just kind of falls out before your eyes, right? And so the way I think of these Hecke stacks and the Hecke operators on bungee is that they package together cohomologies of different towers like this, but in some kind of compressed way, some kind of zip file or something like this, right? It's like, here, like the role of B and mu, right, is somehow disentangled from each other in some way, right? You can imagine taking different stalks of this for different B's, right? Because there could be many B's in this set, BG mu, but this will contain sort of the cohomology of all of those towers in one object. Right.
is it true that in some sense Banshee is kind of modern? It's a tool to to combine together all these.
Yeah. That's the way.
So we start with the Lubin-Tate story. Then we try to generalize it, and the really non-trivial step
That's right.
was to get rid of the minuscule assumption, or I would say the minuscule curse. So Griffiths cursed us with
That's right.
Griffiths satisfied the condition, and somehow they got rid of this curse. But then the next step was to somehow patch together all this information.
That's right.
Because we don't want to, for instance, in the case when we are deal with actual Shimura varieties, we don't want to fix it. Of course, we can fix it at a particular point in a Shimura variety, but we would like to combine all this information together.
Right. It's a new way of packaging some old information. That's right.
Packages all.
So let me write one more formula which would relate to things that I think you've been thinking about for a long time. If I just take the Lubin-Tate tower, just for GL2, right? This has actions of GL2QP and D cross. I can take a representation of GL2QP, right? And you can say, okay, what does the sort of pi isotypic part of the cohomology of this tower look like? And so in this language, I'm kind of just going to specialize this a little bit. So now I'm on Bun GL2, and I had this point earlier that I was labeling this point like 1/2. Take the stock at this point 1/2 of the standard Hecke operator attached to this two-dimensional GL2 representation, and then this pi gives you some sheaf at 1. And oh, sorry, maybe strictly speaking, some shift. Yeah, sheaf at 1. So this gives you some sheaf at 1. You can extend, apply Hecke, and then take a stock. And if this is supercuspidal, so I told you earlier that if this is supercuspidal, you'll get sort of rho box times the L parameter of phi. And I think this is exactly what you basically conjectured, and then Carriol elaborated for GLN, and then Harris and Taylor proved. But in this setting, all the action here can sort of be packaged into these Hecke operators acting on sheaves on Bungie. So maybe that's the moral takeaway for the last half of this lecture, is that the cohomology of these kind of towers that we know we care about as Langlands people is all actually just packaged in some way into the action of Hecke on sheaves on Bungie. And let me end with one sort of moral statement. This can be very hard to compute with, because as you said, the geometry on this Bungie side is really complicated, and even setting it up is hard. So how on earth are you ever going to compute some Hecke operator on GL9 or something like this? Probably as a human you can't do it, right? One reason I like this categorical picture is that on the other side, you can really do computations, because this stack of L parameters, as you said, is some down-to-earth, relatively down-to-earth thing. So you can just roll up your sleeves and start computing homs between coherent sheaves and stuff, and as a human being, you'll do it. The answer will come out. But then on the other side, it turns into some answer that you never could have guessed in a million years. And so I have other examples like that, but I think this is more than enough for this menu. So let me stop here.
Very good.
I have a dumb question. So,
Yeah, sure.
on the right-hand side, if I plug in a B that's not in this couplet set, do I get 0?
If you plug in a B that's not in this Fargues set, you get 0. That's correct. Yeah, the support. Yeah, this is actually a good question. The support of this sheaf will be like contained in the locus EG mu. Yeah, this is not completely trivial, but it's true. But sort of which B's can occur as a type mu modification of the trivial bundle is the question. So this was answered by Rappaport, actually, in an appendix to this paper by Peter that's called on the p-adic homology of the Lubin-Tate tower. Yeah. Yeah. So this is precise. Yeah, the answer is exactly what you want. Yes. Any other questions?
Well, okay, so there's a question from Zoom.
Yeah.
back to the Steinberg story, what are the corresponding objects for L sub 4 delta sub 4?
That's a really good question. Yeah. So again, you should look at Bertolini-Melli's notes. You can take this to whoever is out there in Zoomland. Actually, L sub 0, L sub minus 2, L sub minus 4, L sub minus 6, those all have structures I understand. The positive L's I'm still confused by. When you try to compute their stalks, they get really confusing. On the other side, on the automorphic side. The negative L's all have stalks which are singletons, like Eurex in one obvious degree. So there's an asymmetry when you go from the L's to the other side. So the positive L's are confusing, and the negative L's are clear.
Maybe you can say that to do with your whole Eisenstein series picture.
Yeah, it has to do with this whole Eisenstein series picture somehow. And also the non-triviality of the gluing at these parameters. That's right. Yeah. Yeah.
Can I also ask another question? Of course. Sorry. So, you were saying. So, what is the relation between local and global Shimura varieties?
Well, okay, so that's its own story, right? But global Shimura varieties tend to have these Newton stratifications once you pick a prime, and the Newton strata tend to break up in some way as like something related to a local Shimura variety and a factor coming from an inclusive variety. So this is usually called like the Mentevand product formula or some version of it. And what this often means is that you can express the cohomology of a local Shimura variety in terms of cohomologies of of a global Shimura variety in terms of cohomologies of certain related local Shimura varieties. So there's this nice paper by Haman and Lee recently where they explain a very general version of this formula. And if you stare at this formula, you realize that it unwinds the cohomology of this global thing into two different bits: cohomologies of inclusive varieties, which are still of global nature, and cohomologies of local Shimura varieties, which are of purely local nature. So you can imagine if you know enough about those separately, you can then prove some theorems about cohomology of global Shimura varieties. And this is a paradigm that people have been, exploiting really effectively. I would say since this first Fargues-Scholze paper on like vanishing of cohomology for these compact unitary Shimura varieties. That's exactly the kind of strategy that they implement starting in that paper. And now people have pushed it much, much further. This is just a vague answer, but that's the flavor of how they're related to this picture. Yes?
Could you say something like super brief about item 5 on the menu?
Item 5. Yeah, I can. There's two T-structures on Bungie. One is a perverse T-structure, and it behaves exactly the way that you would want. Let me just write two symbols. So there's a perverse T-structure. When you have a space that's stratified by germs, you know what perversity should mean. It should mean that at each stratum, your star stalks are in degrees less than or equal to the dimension, right? Less than or equal to minus the dimension. But the dimensions are negative. So this is stuff where the stalks at every B are in degrees less than or equal to minus the dimension of this stratum. But this dimension turns out to be a negative number, and when you put in this other minus sign, the negative number cancels out, and you get the pairing of 2 row Newton point of B. So this defines a T-structure on here, which is extremely clean. Verdier duality, for instance, sort of swaps the left and right halves, just like for constructible sheaves on schemes. This functor C psi, the rough Langlands functor, should be T exact for the perverse T-structure on Bungie and the standard T-structure on QCO. So this I also conjectured in these notes based on some like not totally baseless reasoning. Right, and there's another T-structure on Bungie, which is sort of not the classical thing. I call this the Hadel T-structure. And here it's easier to say what its right half is. Its right half is the stuff where on star stalks actually the opposite inequality holds. So this behaves exactly as you'd imagine a perverse T-structure does. This is some funny phenomenon that this other thing exists and has good properties. And this is supposed to match with the perverse T-structure on ISOC G. But the closure relations on ISOC G are the opposite of on Bungie. And so incarnating that one on Bungie gives you something a little strange. So that's the really short answer. Both of them are discussed in detail in those notes.
Which notes?
These Beijing notes on my website. It's called Beijing Notes on the Categorical Local Langlands Conjecture.
Your notes.
Yeah, they're on
On
yes,
your page,
on my website.
Your webpage.
Yeah. a lot of this menu is sort of discussed in there. Yeah. Other questions?
Wait, so sorry.
Yeah.
This thing about the closure relations being the opposite is a
Yeah.
precise statement.
It's a precise statement. It's a theorem. Okay, that statement, even independently of knowing what the closure relations are, was proved by Ivanov and Gleason in a recent paper that's called Meromorphic Vector Bundles on the Fargues-Scholze curve. So this actually gives a new proof that the topology on Bun G is as I described. They prove that ISOC and Bun have opposite topologies, and then it's a classical theorem that ISOC has the usual Newton partial order. So then on Bun G, it's the opposite of the usual Newton partial order. Yeah, there's a good reference.